Spatial and temporal patterns of erosion. In mountain belts, denudation is uneven across space and through time. We will build intuition for why erosion rates vary within and among ranges and how climate and tectonics can change those rates. First, spatial patterns within a single mountain belt. Imagine a north to south transect across a range. Denudation often peaks near the orogenic core, where rock uplift is fastest. In central Nepal, rates climb from roughly 0.3 millimeters per year in the south to about 1 near the divide, and up to 2 to 3 on the steep southern flank of the high peaks. Rainfall in this example is relatively uniform, so the jump in erosion primarily mirrors tectonic forcing from a ramp in the main thrust. Climate gradients can also control spatial patterns. Consider a wet windward side and a dry leeward side of a range. On the western flanks of New Zealand's Southern Alps, more than 10 meters of rain per year drive frequent landslides and very high erosion, about 5 to 10 millimeters per year. East of the divide, in the rain shadow, erosion is more moderate, around 0.5 to 1.5 millimeters per year. Along a very long mountain chain, climate zones change. In the tropical Andes, with heavy rainfall and strong weathering, many basins erode around 0.5 to 1 millimeter per year. In the hyper-arid central Andes near the Atacama, erosion can be less than 0.01 to 0.1, some of the lowest on Earth. Further south, in glaciated Patagonia, rates rise again to around 0.2 to 0.8. Globally, the fastest erosion often occurs where uplift is high and precipitation is high. Think of a simple map: uplift on one axis, precipitation on the other. Regions like the Himalaya, Taiwan, and the Southern Alps sit in the high corner. Arid but active ranges can be high uplift but low precipitation, so their erosion is moderate. Vast flat dry places erode slowly per unit area, yet collectively export lots of sediment because they cover huge areas. Now, temporal patterns. Climate oscillations can speed up or slow down erosion. During glacial times, glaciers carve efficiently above the snowline. Many ranges show accelerated erosion in the last 2 million years, coincident with major glaciations. Tectonic pulses can also change erosion rates, often with a lag as landscapes adjust. A sudden increase in uplift steepens rivers and creates a nick point that migrates upstream. As the nick point moves, incision rates spike locally and then relax after the wave passes. Spatial patterns and temporal changes interact. Suppose uplift is focused in a core zone. If climate shifts to deliver more rainfall there, the high erosion area can widen and intensify. After glaciation, erosion focus may shift from valley bottoms to unstable hill slopes as the landscape readjusts. Key ideas. 1. Spatial variation arises from the interplay of uplift, lithology, slope, climate, and vegetation. 2. Temporal variation tracks climate cycles and tectonic pulses, often with transient responses. 3. Understanding both patterns and their feedbacks is essential to decode landscape evolution in active mountain belts. Thanks for watching.